So these are the design abstraction level. The first one is the device design abstraction layer, in which we will study the construction of transistors, the p-n junctions, the doping, and all the physical properties, all the characteristic equations and all these things. Then the circuit level. At this level we deal with the transistors, capacitors, resistors, and ground, VCC, and all these things. So they are like electronic circuits. And the third level of abstraction is the gate level of abstraction. These are the same circuits that you studied in your DLD. Then the new thing is module level for you. At this level we deal with such kind of building blocks. For example, this is a building block for adder. So inside this module we can have a very complex circuit. For example, it can be a 32-bit adder. So all the complexity is inside this box. So at this level of abstraction we have a lot of modules. For example, adders, we can have modules for multipliers, for arithmetic logic units, for finite state machines. All these are structures that we will study. Okay, then the last level of abstraction, so this is the fourth level of abstraction. The last level of abstraction, design abstraction, is this one, which is the system level. So at the system level you consider all the integration of all the components. It contains all the elements. It is basically a packaged system. Okay, so this is the last level of abstraction. So what are the fundamental design matrices? So basically the design matrix tells if a circuit is better or not. So how we decide? Okay, so the first design matrix is of course functionality. So whatever you design, it should be doing what is intended to do. So the functionality should be correct. Okay, the second thing, design matrix, is the cost. So whatever you want to design, it should be at a cost that the consumer should be able to buy it. So in VLSI design there are two main costs. One is called NRE, which stands for non-recurring expenditure, NRE, and then RE means recurring expenditure. So the NRE cost, for example, is the design effort. So all the engineers that a company has hired, they spend their time, so the company has to pay. So that is the design effort. Also the fabrication plant. For example, I told you before that a 14 nanometer fab is different from, let's say, a 32 nanometer fab. So it costs to develop these fabs. So that is also NRE cost. And this RE cost is variable. So for example, if you want to design maybe microprocessor, so you will need different kinds of material, you will need different kinds of packaging. If you want to design, let's say, ASIC for a media player, then maybe you need different kinds of material and different kinds of packaging. Also note that the testing. So obviously whatever you design, it needs to be tested. And remember that testing is a huge cost. After manufacturing, you have to put a lot of effort in, not even after manufacturing, during manufacturing you have to put a lot of effort. 80% of effort goes to testing. So testing is very, very important, because imagine that if you are Intel and you develop chips that are faulty and you ship it all over the world, then maybe after 1 year or some months a bug is diagnosed. It will cost Intel a huge amount of money. So that's why design is, sometimes they say design is 20% and testing is 80%. I mean, just to emphasize the importance of testing. And there are so many methods of testing. Hopefully we will get to it in this course. Then the other matrix is that it should be robust, because you know that there is this problem of noise. This noise can be coming from within the circuit, because you have all the electronic components, you have the power supply, and there can be switching in the power supply. So there is noise within the circuit which can affect the operation of your signals propagation. Then there can be sources of noise from environment. So for example, nowadays the circuits are susceptible to environmental radiation. So the radiation that is present in our surrounding, that comes from the sun. So these circuits that you use, they are susceptible to the radiation in your environment. So your circuit should be designed in a way that it is robust to noise within the circuits and to environmental effects, for example radiation. And then the other design matrix is that your circuit should be speed. The speed is your highest frequency. For example, you always like 2.4 gigahertz compared to, let's say, 1 gigahertz, because it is fast. So it is basically the clock speed. And then you want the power consumption or energy. So this is because all your mobile devices, you want them to last longer on battery. So these are the fundamental design matrices for a digital system. And then if you are a designer, the other thing is time to market. This means how fast you can build your chip, your IC. So obviously a company wants to minimize the time to market in order to compete in the market. So cost of integrated circuit, again this is in a explained a bit. So as I told you, the design effort of engineers, the design verification effort, I told you verification is a huge part. Then the mask generation, because your mask should be fault free. There should not be, for example, any shorts or open wires or anything like that. So the mask require effort, and these are influenced by the design complexity and how productive your designers are. And if you have small volume, the NRE cost goes up. So obviously that's why these chip manufacturing is a hard business to do. If you want to make chips, then you want to sell it in large quantities to amortize NRE. So you want to balance the NRE cost, and the only way you can balance the NRE cost is to sell a lot of products. And that's how the large companies are there. They are in the business because they can sell, and small companies cannot do it. So, and we talked about the recurring cost. So it is basically the cost of silicon processing, and it's proportional to the chip area. So if your chip is large, the cost will be large. If it is small, the cost will be small. Then the assembly, packaging, it also depends on your chip area and all these things, and its kind, its characteristics. And then you want to test it, so the testing also cost, as I told you. These testings are very, very rigorous. So you want to test it, for example, on different humidity level, because your products may be shipping to different parts of the world, and you want the product to be working in all the different regions. So you want it to work in different temperatures. Okay, you want it to work in different let's say voltages. Okay, so all these different kinds of tests you want to perform. So they are very, very rigorous tests. So the cost of IC is variable cost per IC, which is the RE, and then the fixed cost NRE divided by volume. So if you want to minimize the cost per IC, you have to increase the volume, and if you increase the volume, the cost of IC should go down. So this is a picture of silicon wafer from AMD. I don't know if you know about AMD. AMD is another company which is a competitor of Intel. Okay, I just remember an interesting story. The AMD company was founded by a Pakistani. I don't remember the name, but later on he sold this company. So all the businesses was initially set up by Pakistani, and the designer was also himself. Okay, so this is the picture of a wafer. So you see this whole thing, and it has a large quantity of these small things like this. These are your chips or dies. So they are manufactured in like huge volumes on these wafers, and then they are cut by specialized equipment into individual dies, and then they are tested and all those things. Talking about reliability, so reliability, as I told you, that there are two sources, internal to the circuit and external. So in internal to the circuit, we have this one kind of noise coming from the inductive coupling. So if there is a change in current, so you know the inductors are sensitive to change in current. So when there is a change in current, maybe the change induces some flux here, and maybe this is your circuit that is doing some useful work, so it will get disturbed. Then we have capacitive coupling. This is the second one. So we have a capacitor and the change in voltage occur, and this capacitor can disturb, for example, this capacitor. So this again can disturb your data. And we have, like as I told you, that we have power supply and ground. So they are basically taking your input from AC and converting it into DC. So they are complex electronic circuits. So there may be noise coming from them. So all these sources of noise, your circuit should be robust against all these internal sources of noise. So noise is an unwanted variation of voltage or current at the logic nodes, and I told you that we have two main sources: capacitive, inductive, and power supply noise. Okay, so this is just the explanation of what I have said before. Static gate behavior. So you want your gates to behave the same, irrespective of variation in manufacturing processes, okay, and noise disturbances. So we talked about noise disturbances, but there can be variation in manufacturing processes. What that means, as I told you, that the manufacturing is a very complex process, and they use light to transfer your circuits from the masks to the silicon. Sometimes there can be defects, for example a short circuit or an open circuit, or even sometimes there can be minute differences in the silicon. So the silicon may not be of the same quality. So it is possible that on the same die I have shown, on the same wafer, the wafer I have shown you previously, maybe in the center of the wafer you have chips that are very well manufactured, and maybe at the boundaries of the wafer you have chips where the silicon is not of that quality. So these kind of variation are real, and you want your gates to work even with these variations. Okay, so let's see how these variables are dealt. So a logical how they are dealt with are is with voltage levels. So nominal voltage level. Let's see what that means. So I will explain what is this VOH and VOL in the next slide. Okay, let's go to the next slide. Okay, so you see here this is an inverter. So this is a gate. Inverter is a gate. If you gave it a 0, it will give you a 1. If you gave it a 1, it will give you a 0. So in all your DLD you talked about two things: logic 0 and logic 1. Now what is logic 0 and what is logic 1? Basically they are voltage ranges. So it's very important. So imagine this is the voltage transfer curve. This is the voltage transfer curve of a NOT gate, and let's see how this works. So on the x-axis we have the input, which is Vx, and on the y-axis we have the output, which is V of y. So let's say that I want a 0 to be present on the input. So when I want a 0 to give as an input to the NOT gate, the 0 should be in this range. It should be between 0 volts and VIL volts, where IL means voltage input low. So if I want to give a logic 0 input to my NOT gate, the voltage should be between 0 volts and VIL volts. Now VIL may be, for example, 1.8 volts. So if I give a voltage to my NOT gate that is between 0 volts and 1.8 volts, my NOT gate will understand that it's a logic 0. Okay, so the NOT gate will produce an output, okay, and that output should be above this. It should be logic 1. So the region for logic 1 is this one. Anything above this is logic 1. Okay, so the voltage produced by my NOT gate will be equal to or greater than VOH, and VOH stands for voltage output high. So this is the voltage that will be used for a high output. So for example, I may say that VOH for my NOT gate is let's say it is 3.8 volts. Okay, again, if I want to enter a 1 to my NOT gate, the voltage should be between 0 and VIL, where VIL means voltage input high. So for example, this may be, let's say this may be, for example, 2.8, or let's say 3.2 volts. Sorry. Let me correct this. So if I want to give an input to my NOT gate of logic 1, it should be here. It should be above VIH. So as I say, let's consider the VIH is, let's say, 3.2 volts. So it should be above 3.2 volts. It should be above 3.2 volts. So any input about 3.2 volts will be considered a logic 1. And for this, my NOT gate will produce an output in this range, which is VOL, which means voltage output low. So it will produce an output that is between 0 and VOL. And this may be, for example, let's say if this VIL was 1.8 volts, this may be, for example, 1.6 volts or something. Okay, so now you know that the logic levels are basically voltage ranges, and this is the middle point is the switching threshold, and we have this region where you see the voltage is sharply reducing. Here the gain is very high. So basically this is transistor, and you know the transistor as an analog quantity, it's not digital. So but if you use it in these regions VIL, VIH, VOL, VOH in a certain manner in the cutoff and saturation region, you are using it as a switch. So that is the cutoff and saturation region, and this is where you use the transistor as analog component. So if you are using it as an amplifier, you use it in this region. Okay, so the mapping logic levels to voltage levels. So we have these regions, and the regions of acceptable high and low are delimited by VIL, VIH and VIL, and represents the voltage on VTC. So now you see that if you want to input a logic 0, the range is this one. If you want to input a logic 1, the range is this one. And you see the VIL is higher than VOL. What this means? So for example, this is 1.6 volt. This should be greater than, so for example, it may be 1.8 volt. And here VIH is, for example, 3.2, and VOH is 3.8 volt. What this means is that you hold the sender to a tougher standard. Let me explain this in this slide. So for example, we have these two gates, two NOT gates. This is gate number 1 and this is gate number 2. They are connected. So this gate will produce the quantities VOL and VOH. So if this gate wants to send a logic 0, it will send a voltage between ground and VOL. If this gate wants to send a voltage that is logic 1, it will send a voltage that is greater than VOH. Okay, now coming to, so this is our sender and this is our receiver. On the receiver side, if my receiver receives any voltage that is between 0 and VIL, it will say it is logic 0. If it receives any voltage between VDD and VIH, it will say it is logic 1. Okay, note this. This is undefined region. So this region is undefined region. What this means? This means that if my sender receives a voltage that is higher than VIL and lower than VIH, what will happen? My sender will get confused because it's not 0 and it's not 1. So here my digital gate will fail. It will not work. Okay, because we have violated the gate discipline. So if this ever happens to your gate will be confused. Okay, so this is one thing to understand, the undefined region. And interestingly, we will come back to this undefined region in later course, and for a certain amount of time the people could not understand, but the computer hangs was a result of this undefined region. Okay, so keep this in mind, we will come back to this. So your computer used to get hanged a lot in the old days. Now it's less frequent, but in the old days your computer used to get hanged a lot. So one of the reasons, I'm not saying all the reasons, the reason can be there is some problem with your software or your operating system, but one of the reason is that it's due to this undefined regions. Your circuits are pushed to this undefined region and your circuits are confused, they are sitting there confused. Okay, so we will come back to this later in the course. The second thing that is to be considered is this one, that we have this noise margin. You see, the receiver is allowed to send voltage between VOH and VDD for logic 1. Similarly, the sender is held to send a voltage between VOL and ground. Okay, but on the receiver side, this logic boundary is relaxed. You see, this is relaxed. Why? This is there for noise margin. So if I'm considering the noise margin for logic high, it is equal to what? It is equal to VOH minus VIH. So this is the window or the relaxation for noise. This is how much noise can my logic 1 tolerate. So imagine the sender is sending a 1 that is between VOH and VDD, but on the way there is some noise. Okay, and noise go up, it can go down, so this mixed with my signal. So on the receiver side, if it is between VIH and VDD, then fine, then the receiver can understand that the sender send a logic 1. Okay, so you see here is the voltage dip which will bring it down, so that's why VIH is down compared to VOH. So to accommodate for the noise margin. So this is the fundamental digital abstraction. These are called logic thresholds. So your gate, no matter whichever gate it is a NOT gate, it is an AND gate, it is a NOR gate, it should obey this digital gate abstraction to deal with noise. Okay. So regenerative property. So what is a regenerative property? Basically, this is the consequence of the logic thresholds that we discussed in the previous slide. So a gate with regenerative property ensures that a disturbed signal converges back to a nominal voltage value. So what this means? This means that if you have a long chain of gates, like long chain of gates. So these are interconnected gates, for example here, and over the time the signal that propagates becomes weaker. It becomes weaker. So because of the logic thresholds that we discussed in the previous slides, which is that a gate will always generate for a logic 1 a voltage that is between V of H and VDD. So if during the propagation the signal got weaker, the gate will produce a clean signal. Okay, so that is what the regenerative property means. So for example, consider this, that we have V1, V0. This is the signal which is, let's say, coming from any previous stage. It is weaker. So when it gets passed through you see it is enhanced. The logic levels are enhanced. Ones and zeros are enhanced. So this is due to the regenerative property, and you see here it is fully restored. So because of the logic thresholds, the gates have this kind of regenerative properties. Okay, and this is good because noise is everywhere, so it's a way to deal with noise. The other thing is directivity. So a gate must be unidirectional. What this means, that any changes in the output should not appear at any unchanging input. So the output should not affect the input. As we told you before, that there are different kinds of coupling. For example, capacitive coupling, inductive coupling between the inputs and the outputs. So there is some disturbance. Okay, so practically there will be some disturbance. So how can you reduce that disturbance? So the output impedance should be ideally 0, and the input impedance should be infinity. So if you have, like, this is your gate, so here at the output your Z out should be approximately 0, and your Z in should be approximately infinity. So that's the ideal properties, and which means that if you connect this gate as a driver to, let's say, any other gate, okay, so if the output impedance is close to 0, it will deliver the maximum voltage and power to the driven gate. And similarly, what is the advantage of infinite Zn? The advantage is it will not draw too much current from the driver. So it will not draw too much current from the driver. So I think you may have taken the first course on electronic circuit design, and I suppose you have studied amplifiers. So these are the characteristics These were the characteristics that you studied, that an ideal amplifier should have a Z out of 0 and a Z in of ideally infinity. Okay, so let's